Hi, everyone. It's Tom Keelan here. In this video, I'm going to give you a brief introduction to the Metalogs and ELD Metalogs Excel workbooks, which you can download for free on the metalogs.org website. The purpose here is to enable you to apply the complete Metalog system, which is contained in both of these workbooks, to your own sets of data. And here I intend to show you how. When you first open up the Metalogs workbook, you'll see there's some illustrative data in there. We can go ahead and get rid of that. That's just for something to illustrate the workbook, and we'll come back to it. But if you have no data, no input data, then what you'll see is a message up here that says at least 2 input parameters are required. So let's suppose we're going to be assessing a probability distribution over, let's say, future revenues for a new product. So we can type in here revenues. Let's say it's in millions of dollars. And you'll see immediately that the name you've typed in this cell C9 here appears as the chart titles here. Now, if we started off with our expert and we ask him about, let's say, a new product that'll be that maybe it's already been launched, but we're trying to forecast, let's say, revenues 2 years from today, one might ask the expert, can you give me a number so that there's only one chance in 100 that revenues could be that high? And the expert might say something like, well, I think there's a 99% chance that revenues will be less than, let's pick a number, 85 million. All right, that's fine. And you see there's still a message there saying now that there are at least 2 input parameters are required. So let's ask the question on the other end, what would be a number for revenue so that there's only 1 in 100 chance that the revenue would be less than that number? And suppose the answer was 8 million from our expert. Then we can enter that number. And now we suddenly see that we've got a smooth curve. In this case, since there are only 2 parameters, it's a logistic distribution exactly. It's a 2-term Metalog, it's unbounded, and it goes right exactly through these points. So let's suppose we assess a third data point. We ask him for his 90%. And he might say, for example, that would be $50 million. In other words, there's a 90% chance that revenues would be less than $50 million. We could ask him for his 10%. And he might say there's a 10% chance that revenues are less than 20 million. All right. And now we have 4 points there, and you can see the 4 points on the chart here. You can see that the 2-term Metalog doesn't go through those points exactly. It's an okay approximation, but if we increase the number of terms here in this box, say we use a 3-term Metalog, now we've got something that's actually a lot closer to those points, and you can see the information that the expert has given us is skewed to the right. And if you go up to 4 terms, with a 4-term Metalog, now you get a distribution that goes through, so long as it's feasible, which it is in this case, you get a distribution that goes through all 4 of those points exactly. Suppose we assess now just one more point. Let's say we ask him for his median, give us a number for revenues that's equally such that the actual revenues are equally likely to be above or below that number. Suppose he says 30 million. All right, and now we have a 5th point. The 4-term Metalog does a pretty good job with those 5 points in a least squares sense, attempting to match them. But if you increase the number of terms to 5 terms, now we have a Metalog, and again, this one is feasible, that goes through those 5 points exactly. So it's a very good representation of the views the expert has just provided. This Metalog panel on the right shows the densities that would result from using different numbers of Metalog terms. However, suppose now that the expert says, well, wait a minute, we're talking about new product revenues, and I see that the tail of that distribution goes down below 0. That just doesn't make any sense. So if that's the case, if you want a semi-bounded distribution, you'd change this from unbounded Metalog to a semi-bounded low Metalog. That's SL in this worksheet. And now what you have is a distribution that goes exactly through these same quantile parameters that you've already put in, except it has a lower bound of 0. All right. And so that corresponds better, I think, to what the expert was thinking. Now, he might also say, gee, you know, that tail looks like it extends pretty far to the right on the upper end. It looks like it goes up to 130, $140 million. He said, I just can't see any possible way that the revenues for this product could be more than 110 million. And if he really believes that, and you're encoding it and working with it, you may say, well, let me use a bounded metalog then. And if the expert says there's no way that revenues would be greater than, let's say, 110 million, then you have a bounded distribution that's bounded on the low end by 0, on the upper end by 110, and still has those same 5 quantile parameters in between. So let's take a further look at the information displayed on this spreadsheet. In the first of all, your A coefficients are displayed right here for this 5-term metalog distribution. So there they are for whatever. So you know exactly what those parameters are. We have a field here called quantile parameters, and those are the associated with whatever vector of probabilities you find convenient for interpretation. But here the quantile parameters are 10% chance of being less than 20, 25% chance of being less than 25.6, and so forth. And that is a set of parameters such that if I were to take them and fill them in over here and paste them on top of my input parameter data, you'd find you'd get exactly the same A coefficients. And you can try that yourself. I'm not going to do it now. But the point is the quantile parameters are a nice convenient way to interpret the set of A coefficients that you have here. And those quantile parameters, by the way, if you wanted them to be for different probabilities, you could adjust this here. Suppose you wanted, I don't know why you would want this, but instead of the median, you want a 55% probability in there. For interpretation, you could put a 0.55 in right here, and then you'd see your you'd have the various points that it goes through. But I'm going to go back to 0.5 here. All right. So those are the key features of this so far. Now, there's more information that's provided here. The moments. What are the moments of this probability distribution? Well, as you can see here, they're blank because the moments are in closed form are available only for the unbounded metalog. But if you switch this back to an unbounded metalog, then you'll see that your moments, mean, variance, skewness, and kurtosis are immediately displayed. And then if you wish to simulate from this probability distribution here, you can plug in a RAND formula right here in whatever this is, cell X53. And every time you press F9, you get a simulated value in this cell Y53. You get a new simulated value. So you can run a simulation right off this spreadsheet if you wanted. And then finally, as you likely know by now, the metalog is specified X on this axis as a function of Y. That is, it's in the F inverse form. But if you really wanted Y as a function of X, you can calculate it here. Suppose you say, I want to know what Y value on the cumulative distribution corresponds to an X of, say, 40. You put in a 40 there, and it turns out there's a 79.1% chance that revenues will be less than 40. You could do this for any value you wanted. You could do this for 15. And there's only a 3% chance that revenues would be less than 15. So those are the key features of the part of this worksheet that is displayed here in the information that's displayed. By the way, these A coefficients and these quantile parameters are associated with this 5-term metalog. If I wanted to use a 4-term metalog for this data, I've just used a 4-term metalog. It's a very close approximation. Now you can see that I have 4 A coefficients that are non-zero and 4 quantile parameters. So that's the overall working of this spreadsheet. Now, in terms of the information that's here, column A, B, and to the right of it, these are all the calculations that the spreadsheet does. You can move way over here and you can see quite a few calculations. I'm not going to go over those now, but suffice it to say that these calculations are all written in native Excel. There are no macros, there are no named ranges. And so really all of these calculations here are simply there in order to make this whole spreadsheet work. You don't need to display them. You don't need to have them anywhere near here. And in fact, if I insert columns here, then it pushed all those calculations way over to the right. And now you've got lots more room on your spreadsheet to be able to do whatever work or side calculations you might want to do. So that's the overall introduction to the Metalogs worksheet. Let's turn now to the ELD Metalogs worksheet, which turns out that it's exactly the same. It has all of the same features. It has all of the same calculations in it. The only difference at all is here you put in only your X data, because an ELD stands for equally likely data. And so if you're assuming that your data is equally likely, then you only have to put in your X data, which here happened to be 10 points off of a normal distribution. But of course, you can just erase those and put in whatever data you want. A convention that I use throughout these worksheets, by the way, is that anything in light yellow is input data that you can change. Anything in green is typically something that you wouldn't want to modify, and the light blue cells are optional. In any case, for whatever data you put in on an equally likely data worksheet, you will find that the worksheet itself will assign equally likely probabilities to that data, so you don't have to bother to do it. And that's the only difference between the ELD Metalogs worksheet and the Metalogs worksheet.